Hello, I'm Joseph Utek. I'm the developer on the Cafe project. Sorry I couldn't be there today. I'm at home sick here in Little Rock. I've been working with Dr. Brockhausen for roughly 3 months on the Cafe project. My background is in software development, so in that time I've thought a lot about the architecture of the Cafe project and done research on the performance of RDF triple stores. I'm not in the room, so I can't judge how lost the crowd is. I'll try and stop myself from going too far into the weeds. I don't make any promises, though. So, there's my email. You can tell me how it was, and here we go. The Cafe project consists of 4 major components. First is the actual website itself, which will be written in AngularJS, which is a JavaScript framework. Then we have the 2 semantic web technology pieces, which is an RDF triple store, where we'll keep the data, and then the ontology written in the web ontology language, OWL, which is where sort of the lion's share of the work of Cafe will go. And finally, there's a piece of custom software I'll be writing, which is called a REST middleware. I don't have a good name for it yet. If anyone thinks of one after this, please let me know. I like fancy names. To show you how all this ties together, I've made a quick graph. Like I said, first we have the actual website. This is where everything the users will see. This is where they'll input data about their roles, and this is where we'll display the organogram that the ontology will help generate. Then over here on the far right, we have the actual RDF triple store, where all of the triples representing this data will be kept, and it will actually perform all of the reasoning that the ontology will assist with. It will perform all of the reasoning for the ontology. To help the website and the triple store get along, that's the job of this middleware. And the reason we need this middleware is what I have up here. That this methodology of design this is a client-side web application. What that sort of means is that all of the work of rendering the application and all of the work of keeping it in a state for the user is handled on their side. And so we sort of take the website, we give it to them, their browser does all the work of figuring out how it's going to be rendered and all of that, and it then acts as its own sort of application, and it wants to know data, so it wants to know about these roles, and it will make requests over to the server in very simple forms. It'll make very simple requests. And the job of this middleware is to take the simple requests from the website, run a query, and then return it in a very standard format. This is called, the format it'll be in is what this REST is. REST stands for Representational State Transfer. It is a stateless form of data transmission. What that means is that the middleware doesn't actually care what state the website is in or what state the application is in. All it knows is that the application has asked for this piece of data. So say we have a role, and a role has, or just use a person. So we have a person has a name. So, and it's a very simple application. We just have a person and they have a name. So the application will say, I need to know the name of this person, and it'll have an ID for that person maybe. Or maybe it doesn't. Maybe it needs to know all the people, and it will ask, tell me all the people. And it has all the people, and it says, now I need their names. Please tell me the name of this person. So it'll ask that to the middleware. The middleware will then just return the name of that person. It doesn't care what the website looks like, what page it's on, or anything like that. It just knows that the application asked for information about this user, or about this person. The reason for this is a little complicated. It has to do with a computer science design methodology called the Model Controller View, or the Model View Controller, MVC, which is an attempt to separate how data is stored from how it's viewed and how it's controlled. And this is very much in that vein of design. Client-side web applications are increasing in popularity recently, and because of this, when I sat down to think about how to incorporate an RDF triple store into this environment, there was not a lot of information on the internet or in research about accomplishing this. So my first real quandary was it going to be possible to use an RDF triple store as the backend for a client-side web application? This isn't as obvious as you'd think, because when you have a client-side web application like this, the types of requests that it makes over to the data source are different than when you're using a more traditional design model, where in a more traditional design, you can run maybe a few large queries that say, here's everything I need to render this page of the application, and we'll run one large query, render the whole page out, and then give it back to the user. Whereas with this, the client-side portion over here is rendering the page on its own and asking for little bits of data as it needs it. And it could be, instead of using 1 or 2 large queries per page, it could be sending 10 or 20 or 100 queries that are much smaller and much more focused. Because of this, we needed to know, could an RDF triple store actually return that many queries per second? Is it suitable for large numbers of queries per second, or just running, as opposed to running large single queries and getting lots of data back? I didn't manage to find any real research looking into this, and so set out to test it myself. In order to test this, we decided that we would attempt to replicate this use case, where we would have a large data source, then we would issue lots of queries and measure the sort of average response time for these small queries to see how many queries we could run in a reasonable amount of time to load a page. So we selected a few triple stores. We chose Apache's Jenna, Systrap's BlazeGraph, which was formerly known as Big Data, and Sesame. These were chosen due to their open source licenses and their production ready state. They have 3 slightly different methodologies for actually storing the data, which results in some different performance times. Apache's Jenna has the most simplistic storage model, which is that it stores the data in the fewest forms, and then it performs all reasoning at runtime. And this can cause certain queries to be slower, but it can also cause certain queries to be faster, because it doesn't have as much data to search through when it's actually retrieving the answer. BlazeGraph stores the data in the most verbose manner and does what's called materialized inference, where if the reasoning would infer some relationship, it will actually create in its data store that relationship as if it existed, so that when query time comes, it can quickly retrieve that. Sesame is sort of a middle ground between the two, where it doesn't have as many indexes as BlazeGraph, however it does materialize inference. To simulate the data we would have, we needed a large source of data. I found the Lehigh University benchmark. It was originally designed to test OWL reasoning. However, as part of that, it produced a large set of university-centric data. That's where the university benchmark part comes from. The data consisted of data that you would have about a university setting. So undergraduate students, graduate students, faculty, classes, departments, research papers, all tied together in various ways. The LUBM, Lehigh University Benchmark, came with a series of queries, SPARQL queries, that were designed to test the OWL reasoning capabilities of a triple store or reasoning engine. However, I wasn't particularly interested in the reasoning capabilities, at least not right now. We were more interested in the performance. So we created a smaller series of queries, which were attempting to return small amounts of data. So for example, it would ask for all of the students in a class, all the information about a student, or all of the students who were taking classes from their advisor. And it would issue as many of these per second as it could. And that was the framework. Then, to have something to compare this with, I took the Lehigh University benchmark data and converted it into a relational format, then loaded it into a MariaDB database. MariaDB is the more modern name for what used to be MySQL. MySQL still exists, but since Oracle bought it, the developers decided to branch off and go their own way and renamed it MariaDB. If you ever hear that, now you'll know. Lots of people still call it MySQL, though. And so I loaded the Lehigh University benchmark data into this relational database and wrote a series of SQL queries that attempted to perform the same thing as the Sparkle queries, just to get a rough idea of how well a relational database, which is widely used in this client-side application world. And so if we can, the idea being that if we can approach the same speed as this relational database, it should work just fine. So anyway, here were our results. First, we had the data load time. We took the Lehigh University benchmark data, which was roughly 1 million triples after we generated it, and broke it down into a set of 10 triples that were loaded at a time. All these numbers are in milliseconds, so the totals here, this is where you can see the first difference between the 3 data stores and their different storage models. BlazeGraph took significantly longer than Jena or Sesame due to its large number of indexes and materializing relationships, and Sesame took significantly longer than Jena thanks to it also materializing relationships. Then we have these queries. I don't have a copy of the queries here. They're in the paper, but I can talk about what they do. So first, there was a baseline query. The baseline query was an attempt to figure out just sort of the inherent delay in running a query on each of these systems. The query was asking for data it itself provided. So really, it wasn't measuring data access time in any way. It was only measuring the latency in a system, as far as seeing a request had come in and returning it. Jena and Sesame performed this in 8 milliseconds, and BlazeGraph performed it in 38 milliseconds. If you do a quick peek ahead, you notice that BlazeGraph consistently was over 30 milliseconds. Query 1.5 is a little special. I'll explain it in a second. There was something causing BlazeGraph to have a 30 millisecond delay at all times. We could never figure this out. It's possibly due to its query optimization engine. It could be due to something else. However, there appeared to be no way to eliminate it, and so it sort of knocked BlazeGraph out of the running as far as usability, as 30 plus milliseconds per query is too many when you're talking about running maybe 20 queries per page. When you're looking at the numbers, Query 1.5 is special, as Query 1.5 was a modified version of Query 1. Query 1 was the only query that caused Sesame to produce a very large result, which is because Query 1 used the optional keyword in Sparkle, which is known to cause problems sometimes. In BlazeGraph, it did not cause a problem. BlazeGraph, yet again, with a 30 millisecond time added, it returned in about the same time as any other query. However, Jena and Sesame both had major problems with the optional keyword, and so Query 1.5 was another version of that query written without the optional keyword. However, because of that, it had to run 4 queries. So if you take the number here and divide it by 4, you'll see the runtime of each individual query, which is closer to 7 or 8, and yet again for BlazeGraph, just over 30. Sesame had the fastest results overall, yet again due to its already materialized inference and low number of indexes, which the number of indexes should decrease query time, but perhaps there's something in that that's also causing BlazeGraph to have problems. Queries 3 and 4 required inferences to be made, which is why Jena was significantly slower than Sesame and BlazeGraph, because it had to perform the inference at query runtime. So how did this compare to the relational database? You can see down here, the relational database was extremely fast, with in between 5 and 6 milliseconds runtime for any query for basically any query I could give it that wasn't intentionally slow to try and tip the scales. So if this is the number we're aiming for, this 5 or 6 milliseconds, you can see that Sesame and Jenna in certain conditions were producing queries that were within that same range of a relational database, which led me to the conclusion that yes, an RDF triple store would be usable as the backend for a client-side web application. Anyway, this went a little longer than I intended, so thank you for listening. And if you ever think to yourself, I should give a video presentation instead of writing up notes for someone else to give a presentation for me, this is about 40 takes in. Thank you.